Okay, good afternoon to you all. Welcome to this session on overview of big data analytics. I'm Kapil Oberai. I'm faculty with the Geoinformatics department at IIRS. So in this session, we'll talk about uh, big data and its characteristics. We'll also look at the various types of big data that we encountered in terms of structured, semi-structured, and unstructured data. Followed by, we'll also have a look at what we mean by big data analytics and what are its various types. Later on, we'll move on to the how does this big data relates to our geospatial data and what are the various challenges. Followed by looking at the various frameworks, big data frameworks that are available for the GIS. There are two prime frameworks named as Hadoop and Spark. And finally, we'll also talk about the role that cloud computing plays for handling that big data and what kind of a support the cloud platforms offers for handling and analysis of the big data. Now, talking about the term big data, so we are aware of the term data, which means the raw facts, and the data are the essential ingredients which are required for any decision making. In fact, data is one of the components, as you learned in the GIS system. Also, the ability to make these data-driven decisions is very, very important for the businesses instead of going for the pure gut feeling kind of a decision making. Now, when we talk about the term big data, the first thing that comes to the person mind is the size. Big means is size. But looking at the size as only one of the dimensions to define big data may not be a good characteristics, because the size is primarily relative and will vary over a period of time. However, the size or the magnitude is a very, very important component which has to be handled purely from the size perspective, the amount of data that we need to handle. So when we talk about big data, we are not only talking about the size, which is one of the dimensions, but there are other characteristics denoted by V's, or the word starting with the alphabet V, to denote the big data. Now we know that there is a huge amount of data being captured, and this slide talks about the amount of data that is generated on every per minute basis. That could be the amount of searches happening on the Google, the people using Facebook, Twitter, and other kinds of social media platforms are available. Now, what leads to such explosion of data in the previous few or more than a decade or so is that the penetration of the internet has gone to the grassroots level. The smartphone availability is also there. So moving from a simple web 1.0 way of consuming the data to the web 2.0, where the users are also contributing the data through social media and other platforms, has led to this whole what we call as a data deluge era, where we are collecting a huge amount of data. So there was a time when we were looking for collecting data, but nowadays there is a huge amount of data is being captured, and such data sets, even we talk about the big giants like Google and Facebook's, where they are looking for catering to these data sets, so they are able to make some informed decisions. That could be recommending the videos to the user, or maybe helping their these data sets, using these data sets in their business. Now, some of these social media platforms also allows us to capture the geosocial data, which we can also use, and these do find their use cases during disaster, and also for product reviews and other kinds of use cases are also available. Now, just to have a look at the amount of data. So as we say, that data is the new oil, which means the huge amount of data is being collected, but we do need to refine it so that we are able to monetize it and use it for a decision making. So in our school days, we were aware of the terms like bit 0 and 1 or nibble or 4 bits. Now nowadays we are talking in terms of terabytes or petabytes and exabytes. So the amount of data that is being generated through various platforms, wherein the geospatial data is also one of the components, is increasing on a year-on-year basis. So this is one projection from International Data Corporation, which talks about that the annual size of the global data sphere will be around 175 zettabytes. So zettabytes, just to talk about, is 10 raised to the power 21. So that you can see the number of zeros followed by 1. So this we are talking purely from sense of the amount of data that is being collected. So amount of data that is generated, that is one aspect, which anyway is a challenge for handling, which means that working on a simple personal computer or a laptop with limited RAM and storage may not be the way to go. So we have to look for more distributed and parallel systems for handling the data. Now, other things that we should also look at is that the data sets that we are talking in during this big data era is that there is a huge amount of data which is primarily semi-structured, or most it is unstructured data. From the relational database perspective, we are well versed with handling of the structured data. So the moment we say structured data, we are talking about data sets that have a well-defined structure. Maybe data is organized in the forms of rows and columns. That could be maybe an Excel file having the various columns, and each row denotes one instance of record in that file, or it could be a comma separated files where again we could have a header and each values or each row are comma separated. Or from the relation database perspective, we could also use a term called schema or structure, where for storing information about, let's say, a student, we will have a student ID, student name, his date of birth, address, and so on. So once the data is structured, it is easy to organize and easy to query and retrieve. But if we look at the data sets, like data coming from a social media platforms like post from Twitter or maybe a Facebook, those kinds of thing, where the data does not confine to a proper structure. We can't say the first line will be some header, second line could be some talking about some event, or third maybe a more like a description. So because it is possible in, for example, if we talk about Twitter, we have roughly let's say 280 character to be used. So this whatever the user who want to post can put whatever he wish to post into that limited character length. Similarly, in the Facebook post, the user can follow any kind of a structure to fulfill. It does not confine to the structure. So now it becomes a problem how to extract meaningful information from such kind of data sets. Now there is something in between which is called as the semi-structured data. So as the word suggests, semi-structured means data that has both elements of some structured format and some which are arbitrary. A good example is the phone diary, wherein we could have a, for each, let's say, a page in the diary, we are storing information about the name, the address, the phone number. However, what the notes you are writing will be arbitrary. Similarly, another example is, let's say, the email messages, wherein the from, to, the subjects could have a structure. We know that these fields will be there, but when we talk about the body or the main email content, that could be primarily unstructured, because the user can put whatever he wish to in the body part. It could be a table, it could be an image, it could be bullet points, and so on. Now, one of the good example of semi-structured data type is called as a JSON, which stands for JavaScript Object Notation, which uses key value pairs for representing the information. As you can see on this slide here, we are storing, depicting information about a person having a name, the first name and the last name. As you can see, the first, this in the quotation mark, first name is the key and the value is the name of the person, let's say Jane. Similarly, last name. Address is a composite field where we are storing an object, let's say street, city, state, zip code, and hobbies is again a multiple value. In this case, we are storing as an array. Maybe this person has two hobbies of surfing and coding. There are other examples of semi-structured data. XML also comes under the semi-structured data. So if we look at from the data perspective, the structured data, as I said, is we are well versed and we are able to handle with the traditional database system which can store and manage this data. But now talking about this semi-structured or this unstructured data is somehow very difficult to put them into the relational based system. So hence there are new kinds of data storage mechanism has come to handle such kind of wide and diverse kind of a data types. Now coming back to the big data characteristics, so we talked about volume. Yes, we've seen that in the past many years a lot of voluminous data is being captured, but that is only one dimension to the big data characteristics. So big data is primarily defined by the V's. Initially there were three denoted by volume, velocity and variety, called as the three V's. Subsequently, one more term was added called as veracity, and then now pretty much in the literature you will find that most people use these 5 V's to denote the big data, which is volume, velocity, variety, veracity, and the value. So let's see one by one what we mean by these terms. So volume denotes the amount or the magnitude of the data sets that are being captured from various sources. Next is the velocity, which talks about the frequency or the speed at which the data is being generated and that needs to be processed. So we are aware of the batch based system where we, let's say example of a payroll processing where we do it at the end of the month. But what if the continuous feeds of data, let's say from social media or from IoT devices are coming, then we need to have some different mechanism of storing, capturing, and also for analysis. Variety, as we discussed, is structured, semi-structured, and unstructured data. Also leads to a lot of, let's say, we require a new way of organizing the data so that we are able to handle such diverse kinds of data sets, because it is not possible to convert these semi-structured and try to put them into a structured. So that is also some of the criteria that we need to consider. The next is the veracity, which talks about the reliability or trustworthiness of the data set, especially from the, let's say if we talk about data sets which are coming from the social media platforms. They could be biased because one example could be that, okay, not all people are maybe putting that information, only a particular demographic age groups will be putting that information. So we have to use that data sets also with bit of caution. And finally, the main aim of this whole data collection is to make a value added business value. So the reason we are doing this big data analytics is to extract the meaningful value or information so that we can take some informed decisions. Now these V's are not independent. So if you look at it closely, we'll see that any increase in one dimension, let's say the velocity increases, obviously the volume will also be increased. Similarly, if the types of data also increase, which will also leads to the increase in the volume. So they are also not primarily independent. They are also in a way dependent on the others. Now, this is a characteristics that makes the big data difficult to capture, store, maybe also retrieve, analyze, and also the visualize, because it is very difficult to visualize, let's say 1 billion points on at a one time on a screen. So we require different ways of representing the data sets. Similarly, processing of the batch versus stream is a different consideration. Similarly, in the case of handling the variety, veracity, and also for extracting the value, how we can store it and how we can able to retrieve and manage it. Okay, having talked about the big data characteristics, the various V's, now let's come together and then let's see the definition of the big data. So big data is defined as huge collection of various data sets which are primarily difficult to process using the traditional data processing platforms, uh, or the state of the art approaches of data processing, which we means by using a typical database or relation database system for storing and managing the data. One more definition which more clarifies this is that big data is a term which we use for collection of data sets. Again, the term important is large and complex. So again, remember, when somebody talk about big data, it's not only about the volume, but always remember the other 5 V's that we have talked about. So which is where volume, obviously, yes, is a one dimension to which adds the complexity, but more complexity is added the moment we have the speed, the velocity, and also the variety of the data. So we'd use the term large and complex to handle using on-hand database management tools or traditional data processing applications, which means it also talks about the storage and also talks about that these kind of data set will be very difficult to analyze using a desktop or a laptop based things. We have to move from a single node to a distributed kind of an environment. Now, after talking about the big data, let's talk about what we mean by big data analytics. So the big data analytics terms means we want to examine again the large and diverse data sets, in this case structured, semi-structured and unstructured. The aim is to uncover the hidden patterns or insights from the data sets. So when we talk about analytics, it's primarily about extracting patterns and insight from the data. Since we are talking about big data, so big data analytics means uh, getting insights from the big data. So we can define them into these types, which are text, audio, video, social media, and also the predictive analytics. When we talk about text analytics, we are looking for extracting information from diverse and vast amount of data sets. In this case, an unstructured data set. An example are for extracting information from blogs, survey posts, so that we are able to serve our end customers in a better way. This is more from the business perspective, or also using maybe natural language processing to make sense of the data sets. The second type is the audio analytics. Here, it refers to analyzing and extracting the information from the audio sets. Now, this is very useful for industries like the call centers, and also you'll find use cases in the healthcare companies where they are primarily trying to understand from the speech patterns, the neurological and the mental related kind of illnesses. Video analytics, again, a very uh, interesting area which talks about analyzing and extracting information from the videos streams, and this is primarily a big focus during the video surveillance kinds of application. Social media analytics is a separate category which primarily is a subset part of a text analytics, but since the focus here is more on analysis of the data from social media, as we have talked about that the media platforms like Facebook, Twitter are the places where people go to for share their opinions, and this becomes a good source for usage, what people are talking about the products, services and other things or events that is happening, uh, to make sense it and use them in our business or other day-to-day use cases. For example, you will find in the literature studies where people are using Twitter data sets for extracting information about traffic patterns, or also usage of these social media platforms during emergency, which is the place where people generally go for sharing the information. So there are good use cases where such information could also be extracted. Now, some of these social media post also allows us to geotag the information, so then we can also have information related to that particular location, or sometimes people also mention the place name, which could also be maybe geocoded to extract the information. The another category is a predictive analytics. As the name suggests, here we are looking for predicting the future outcome based on the past and the current data. Here we make use of various algorithms like decision tree, linear, logistic regression coming under the machine learning gamut. Now, if we talk about the big data process, we could define them into two categories. One is related to the data management, second is the analytics. So before we can analyze the data, we have to make provisions for data storage, recording, managing it so that it could serve our purpose for analysis, where we are looking for a retrieval of the data and also for getting insight or the patterns. So the data management involves steps like acquisition, recording of the data from various sources, followed by data pre-processing like extraction, cleaning, because we are dealing with different diverse data, so we have to integrate that. Sometimes we need to aggregate the data to based on the requirements. Once the data, so data management storage is one component, followed by the other component which is more about the analytics, where we are looking for understanding the data by modeling the processes and carrying out the analysis, and then followed by interpretation of the results, could be in the form of charts or tables and so on. Yeah, so this figure shows the, in a higher level view, the typical workflow that we follow in carrying out this big data analysis exercise. So the data from various sources could be in-house, like from the DBMS or from the warehouse perspective, and also from external sources, data coming from in the form of streams are all collected, leading to the data management role, which is more about, as we talked about, a pre-processing. It could be filtering, cleaning, aggregating some data we need to transform or normalize so that we are able to have all data sets into one format, followed by the modeling process, where it involves selection of the, let's say, the algorithm, estimating the parameters, training the model on the test data, dividing our data sets under test and training and testing, followed by the validation using the test data, followed by the model scoring, where we talk about checking the data on the new data sets, wherein we are either we can use these various spatial big data algorithms like clustering, classification, regression, association, or maybe for the finding out the shortest path kind of thing, we can also do the network analysis. Once the model has generated the results, the next aim is to understand and interpret the results. So this is where the result analysis and visualizations comes into the picture, wherein the user now is to understand and make sense of the data. Now, in case some of these results does not make sense, so which means we need to go back to the modeling step to again train the data in with other diverse data sets, followed by validation, and again checking on the live data sets. Or if some of the results are not better, or we want to include more data sets, we can go back again to the data management and maybe perform some other pre-processing, or maybe aggregate data sets at different scale and again feed it to a model for further processing. So primarily the categories of analysis could be described either descriptive, which means modeling the past behavior, or it could be forecasting like a predictive, or could also be a decision support like prescriptive, which means what the user should be doing. This is more like a decision support tools that that assist the user in what to do next. So the from the modeling perspective, there are various algorithms that are available that the user can use depending on the data sets and also what you want to do, whether classification, regression, or you want to look for pattern and other things. Now, having talked about the big data, the various dimensions, the analysis, the various, let's say, types, let's now come into the, from our geospatial perspective, how does this big data is playing a role and in how it is very important. So the geospatial big data, again, we can define that the data sets that exceeds the capacity of the current computing system. And we also know that the geospatial data is very, very important for various societal applications. What you're seeing here on the above is the infographic showing the Millennium Project 15 challenges. Now, what you are shown with the uh, covered with the rectangle are the areas where the geospatial data plays a very important role. That could be sustainable development, climate change, clean water, population resources, health issues. So these are the areas wherein this big geospatial data has a huge role to play to to solve these kinds of challenges. Now, this Millennium Project has been replaced by a Sustainable Development Goal, where there are 17, which are 17 in numbers, and again, all of them required one way or another the input from the geospatial big data. Now, let's also cover what are the various sources of our geospatial big data. The first is obvious one is from the data sets coming from Earth observation or the remote sensing data. So again, we have diverse platforms, and also the various kinds of sensors parameters like spatial, temporal, spectral, that also makes qualify geospatial data from this our V's perspective coming in the category of geospatial big data. The other kind of data sets which are also contributing to this whole gamut of geospatial big data sources is the data that is coming from surveying, and also the products or mapping products that we are creating for various kinds of use cases. The third kind of a data set is called as a location-based data. Now, these are talks about the GPS traces data that people are also using, which talks about the location, how the mobility and other things people are also using nowadays. One type of location-based data that which is also a source uh, for this geosocial data is called as the social network data. So these are the data sets that are coming from social media platforms like Facebook, Twitter, which could be geolocated, which again, as I said, people use it for sending their views, opinion, events. So this also contribute to the huge voluminous data and also the different types of data sets. The other type of data is the Internet of Things device or IoT sensors, which the people have installed on the ground, which are beaming very frequently the information that could be temperature, precipitation, it could be measuring of the traffic situation and other kinds of information. So if you see all those different sources from satellite imageries, which are again, if you talk about ISRO is one agency which are having their satellite system, but there are other global agencies which also are having their own satellites in orbit. So this is the whole huge amount of data sets that are being captured, generated. Similarly, we are doing other data sets like surveying, the mapping, location based in IoT devices, social networks are whole contributing to this big data sources. Yeah, so this infographic shows the voluminous part from our satellite data perspective. Now this is showing only few of the sensors like Landsat 7, 8, MODIS and the Sentinel series, but obviously there are more sensors. So just to give a glimpse, that somewhere in 2019, maybe the size were around 4 petabytes or so. This is on the yearly data volume. Now if you compare for the data sets from agency perspective has to be maintained over a long period of time, so that we can do some climate change studies, the change detection based studies, so that we can use it for proper planning of the cities and regions and so on. So from the agency perspective, they also need to hand way for handling such data, and also from the user who want to carry out such study, he will also be have a need a way where he can organize so that he can make some analysis from such data sets. So from the analysis perspective, as we said, maybe what we required is a distributed way for analyzing such data sets, because these kinds of the data that we are talking about may not be confined to one laptop or a one PC. So what we required is a scalable and a distributed framework which allows to process such data sets. Two of the popular frameworks are Hadoop and a Spark. So first let's talk about the Hadoop system. So Hadoop is a software framework. Now it is an open source product which allows storing and processing of the big data on a clusters. So when we talk about cluster, we are talking about a group of systems which are connected and then which performs the task, and to the user they appear like a one system. Hadoop primarily has two components. One is about the file system to organize the this vast and diverse data on a fault tolerance and a scalable system that we call as the HDFS, or Hadoop Distributed File System. The second component is called as the map reduce, which is the programming paradigm uh, for scatter or gather or divide and conquer kind of an way for processing such kinds of data sets. So Hadoop distributed file system again runs on a cluster and provides high access to the application data. What it does, it divides a file. Let's say a large file is there, and there is a multiple nodes are there. As you can see, D1, D2, D3, D4 denotes the node in a cluster. So that let's say a file may be divided into 3 blocks, like A, B, and C. So now to increase the fault tolerance, what is happening is the data sets are replicated, primarily a multiple of 3, and the copy of the data sets are kept at various nodes. So which means that in any situation, since in the Hadoop primarily works on commodity systems, not high-end systems, so there's a chance of the system or a node getting failed. So even if the node goes down, still because of the replication, the fault tolerance is there, the application still is online and the process can go on. Now it allows us to store the structured as well as the unstructured data. And then, so this is the first part, which is the base for this Hadoop platform called as a distributed file system, which organize the data, break it up into small pieces, organize in various nodes of the cluster. Once the data is organized, the next part is the programming paradigm, which is the map and reduce. So the problem is divided into 2 phases. One is a map phase, which is the large problem are divided into smaller pieces, and again which are sent to the various nodes where the data is maintained. Now one of the term that we'll encounter in these kind of frameworks is called as a data locality, which means now the code is running where the data is available. So instead of sending the data to the code, we are trying to send the code to the data. So because we know that the CPU is very fast, whereas the IO cost is very, very slow. So hence in such distributed framework, the aim is the data locality. So the code runs on the node where the data resides. So think for a while that there's a larger task which is broken down into smaller pieces where each node runs a part of that task based on the data that resides on that node, followed by the reduce phase, which is the output of this, the subtasks which are handled by different nodes working on their local data sets is sent to the different reducer, which primarily aggregates the data and then stores the result finally for the end user to use it. So the large problem is broken down into smaller subsets. The part of the problem runs on each and every node, and then the reduce steps, which could be again one or more than one, again runs on the once the map task is done, which primarily organize them, aggregate the data and given to the end user. So this is the one part of the map and reduce. So let's try to understand this taking example of a raster imagery. Let's say we have a DEM, which is a very large file for a particular area. And then again, the files are broken down and stored in a fault tolerance in a Hadoop cluster. Now the each tile, we can divide them into different sizes, and each tile is passed to one of the mappers, or let's say more than one mappers, which is processing that tile. And finally the reducers collect those tiles and the final output is returned onto the disk. So this is a good way of dividing the task and again conquering it, or scattering the job and then gathering it. So these type of phrases you will encounter when we come to these kind of a distributed frameworks. Now one more thing that we have to look for there's Hadoop also have a ecosystem of tools and utilities. For example, HDFS provides the fault tolerance storage mechanism, right? MapReduce is the programming paradigm for building it up. but there are other tools that works along with it. For example, we could use a NoSQL system, again an HBase, a columnar based system for storing. We could also use a Hive kind of platform which provide an SQL interface for storing, let's say a warehouse kind of application, developing warehouse application on the top of the Hadoop. Similarly, for machine learning, we can make use of a Mahout library. So there's a whole ecosystem of tools and components that can work with the complete Hadoop ecosystem. Now, one other framework from compared to the Hadoop is called as in Spark. Now, one thing about that Hadoop system is it primarily is good for the batch processing. That is point one. And second thing is it reads and stores the data onto the disk. So it can't do that in memory computing, which is where the Sparks comes in, and this is very good compared to the Hadoop system because it can do the in memory computing. It provides a kind of a data sets called as the resilient distributed data sets, or in the Spark later versions called as the other option of data frame is also provided, which is nothing but a in-memory data storage, which however that could be also stored onto the disk. Now, as we discussed, compared to the Hadoop system, Spark provides multiple advantages because it does not read and write to the disk for each and every time. Because if you have seen the previous slide where I talked about map and reduce, the output of the map job is again returned to the disk, which is read by the reducers, and again the final gathering is done, and then again it is returned to the disk. And we know that the reading writing of the disk are slower compared to the, let's say, the processing that happens in memory. Again, for especially if we talk about spatial data where we have a whole chain of processes to be done, not one after the one followed by the another, this again will be a benefit because Sparks just execute the job only when it asks us to do. So it is something called as lazy evaluation is something the term is used. Now, another good thing about the Spark framework is that uh, it is called as a unified data processing engine, wherein it supports Spark SQL for doing structured data processing, Spark stripping for stream processing, MLib is a library for machine learning, and GraphX is a library for doing graph-based processing. On the top of that, the Spark can work on various kind of data sources. It can run on the top of Hadoop system, or we can use some NoSQL systems also as a data source. Now, other advantage of Spark is that it provides multiple programming language support compared to, let's say, the Hadoop system, which primarily works on Java. The Spark also exposes the APIs which we can use from in Python and R. So hence it is called as a unified analytics engine wherein it supports various kinds of requirements compared to Hadoop where we need to install those separate libraries which I was showing the ecosystem in the previous slide. Here they all come bundled in, which means for structured processing I can go with the Spark SQL and so on. For the other kinds of requirements are all built in into the framework instead of installing and configuring them as the requirement may be. Now, the other types of technologies from the big data system is called as the NoSQL systems. Now, NoSQL system provide a variation or an alternate from the relational model, because we said that the relational models have a predefined structure wherein the data are organized, which means there is something called a schema is there first, and the whatever information we are trying to put into the system should confine to that schema. Whereas NoSQL provides us alternate solution to the relational model, and compared to the relation systems which are primarily, let's say, scale up model or a vertical scaling, they are primarily support scalability through horizontal scaling. As you can see from the figure here, suppose we have purchased a server, the number of traffic increases. So what we can do is we can increase more RAM, more CPU, more hard disk. But again, there's a limit of how much you can scale up. However, from a distributed perspective, it is easy to add new nodes as and when the requirement increases, and we can cut it out as the requirement comes down. So they are primarily built from scalability and performance perspective. Now the types of NoSQL systems are columnar based. It could be graph, it could be key value pair, and there are also document based system like MongoDB, which allows you to store uh, documents like JSON file or CSV file and work them, and also have a support for the geospatial. So we can carry out our geospatial based location search, KNN search can also be done. Now these kind of data, these kinds of NoSQL system provide us to store these diverse data sets in a scalable and a fault tolerant manner. Now there are other such solutions available for uh, for handling such geospatial big data. A few of the example we'll see. One is this spatial Hadoop, which is a variation of the Hadoop system using the MapReduce extension, which is designed to handle the spatial data. So it supports the various spatial data types, the indexing, and good thing is there is a good amount of tutorials are also available. And if you want to get started, you can go to the download section where they also provide the virtual machine environment for you to install and configure. The other kind of system is called as GeoTrellis. Now this is primarily based on the Spark system, which allows you to handle the raster datasets and some capability for the vector, but mostly for the raster datasets we are able to perform at a high scale. The other systems that we wish to should discuss is the call as an array database, or a rasteman is a name of the product. Now, good thing about such kind of systems is it provides us to store and manage the data sets, let's say in our case the raster, in a form of array. So we can think in terms of a data being organized in a form of cube having various dimensions of latitude, longitude, and time, and allows us to perform operations on our raster imagery, either maybe trimming or subsetting of the data sets look from the cube perspective. So we can slice on a particular dimension, we can have a subset of the data sets is possible. The second thing about this array database in this example is the rasteman is it also supports the OGC standard of web coverage service. So once we store our data, we should be able to retrieve the coverages or the rasters following the OGC standards of get capabilities, describe coverage, get coverage kind of URLs or functions we can use. Further, it also supports kind of a query system called as a web coverage processing service, wherein the user can use a declarative language for performing operations on the data sets. For example, let's say we have a coverage stored into the system and we wish to perform, let's say, the NDVI computation. So it provides this kind of a query interface wherein we can write an expression for getting the zero band, let's say the NIR band and the red band, divide by NIR plus red to retrieve the NIR information. So all these things is happening locally. So compared to other system where we need to read the files from the disk, then perform, think in terms again from data locality, the query is running where the data is. So we don't need to move data in and across. Another example is subsetting. For example, we can say, okay, we wish to see only the 500 rows and 500 columns and show us in the form of an PNG. So think in terms of, because the whole data sets are stored at one location, instead of copying and downloading the data, we are able to perform that operation there itself, and only the results we are able to show it to the user. So what we can do here is we can use this as a raster data engine for powering our web-based or mobile applications, wherein it could be performing some decision support system or some analysis can be all done from a server-side perspective, where the user can only get the desired information that he is looking for. Now, because of this data locality principles, such kinds of let's say storage models are fast and can give you also the concurrency and lower with the lower latency. So now you can build using this raster engine as a backend. You can build various application that could be, as we said, coming over the decision support system. You could implement the weighted overlay, or you can implement the AHP, and finally the weighting could be done at the backend using this declarative language, and the results could be displayed to the user interface, which could be a web application or a mobile application. It could even be a desktop based applications. Now, one more type of system that we worked recently as a part of the student work was called as SQL and Hadoop. Now, Hadoop system primarily way of retrieving data is to write the MapReduce kinds of statement. But there is also type of systems like Presto, Hive, and from the Spark perspective, Sedona SQL, which allows us to write it again the queries in the form of an SQL. So what was done was these four were compared based on the varying data sizes and also with the various kinds of queries and also changing the nodes. So one we try with, let's say, 1 node, 2 node, 3 node, 5 and 7 node, and we have seen, so this is showing the with the larger 7 node system and comparing the various data points, and we based on this comparison we find out that out of all, Presto was giving the low latency in terms both by varying the sizes, checking the different kinds of queries, which could be range queries or nearest neighbor queries. And the other important thing here is now these kinds of SQL Hadoop system can be so these can be 1 minute. Yeah, so these can be used for powering our, let's say, the dashboard kind of application wherein the data sets can resides on the backend these SQL Hadoop systems, and then we can run those interactive queries, and interactively the whole dashboard will change. So this is showing a crime analysis wherein selecting on a particular region, the number of crimes in that regions and how many arrests were made, the various category of crime in that region could be done. So you can drill up and drill down, that kind of operations could be done. Now I want to also talk about the role of cloud computing and what way these kinds of cloud-based systems, let's say, are useful for running such big data operations, because we need to store and process this large amount of data, and then from the organization perspective they may not have the infrastructure necessary in place. So this cloud based technology provide the underlying platform wherein the data could be handled. Now the good thing about cloud computing is provides a pay per use kind of a model where we only use the system for the time that we are utilizing it. There are various kinds of service model. We could have an infrastructure as a service, we could have a platform, and also as a software. So when we talk about infrastructure as a service, we are talking about it's like a renting of a hardware infrastructure from a cloud provider, which means now the cloud provider is managing the infrastructure. We don't need to manage it, making a live 24/7. That is something the user can, the cloud provider is doing. We are logging to the system and trying to use that as a virtual machine environment. On the top, we can install the various software platforms that we wish to use. The other example is a platform as a service, wherein suppose you want to use this Hadoop cluster. So instead of configuring yourself, you could have directly a platform available, Hadoop configure, Spark configure, and on the top you can build some application. The third type of service model is called as a software as a service. So as the name suggests here, the cloud provider handles all the parts from infrastructure to platform and also the solution, and users only maybe log into the web browser and use it. Example could be mailing solutions, CRM solutions, let's say GIS solutions are all can also be a part of the SaaS. So yeah, so this infographic nicely covers about the how does the big data and cloud works together. So cloud infrastructure provides the necessary underpinning on the top, providing advantages of cloud, which is on-demand self-service, scalability, rapid elasticity, resource pooling. Whenever we want, we can scale it up. Could be access on various devices, and it is a measured service, which means we are paying only for the amount of we are using. And then these kind of platform, big data platform, or some are available if you go with a platform as a service, or we can also install them. And then these can handle the diverse amount of data that we talk about, from the volume, velocity, and veracity, because these are scalable solutions. So they could be able to handle such diverse data sets. And then we'll also take over the management, access, analysis. And from our geospatial perspective, we could build various kinds of applications for the benefit from the value perspective. Decision support could be climate studies, urban studies, land use, land cover, and various smart studies, urban management, and all kind of studies could be done. So the cloud computing provides the critical support uh, for the big data, so that we can do what we are looking for, the value, getting value out from this big data perspective, considering and could have use cases from various domains. Now there are various cloud-based geospatial solutions are also available. Very popular is the Google Earth engine, which the students now prefer to work on. Advantage is, now if you see the processing pipeline from the remote sensing data processing perspective is, so we need to download, perform the pre-processing steps, which are geometric correction, radiometric correction, and other corrections before we get to the actual usage of the data sets. Now, what does the Google Earth engine kind of system performs it? The data are already ingested and are in ready to use format. The whole gamut of data sets from the open source are available. And also remember, the data locality we talks about is the algorithms also runs on the cluster environment, and they provide APIs that could be in the form of a JavaScript or a Python. So they provide a editor. In here we are showing an image of that, where the user can write the snippet of the code. The algorithm and the data are fetched and executed, and all done on a scalable solution. Now, using such kind of platforms, the various kinds of applications could be developed. This is one of the classic example of a these cloud-based platform, which is a time-lapse animation. So here we are talking about long time series of data, let's say 1984 to 2011, because if you want to see the glacier retreat, we have to uh, uh, handle such kind of diverse data. Now, if you compare this with your traditional way of remote sensing data processing, so there's a lot of time will go into the downloading and pre-processing of the data. And then with these kind of platforms, the data sets availability, algorithm availability, the such kind of applications, right, glacier retreat, or maybe checking the deforestation, could be done in a rapid manner compared to a traditional way of data processing, which we do on a laptop or the desktop. So these kind of platforms are the basis on which such large scale studies could be done, where the user can focus more on the analysis or the value part for using the outputs in various use cases. Now finally, let's also talk about few of the challenges that are there for the geospatial big data. Now, one challenge is purely from the computing perspective, because we need to manage and store such large data. So what we require is easiness in accessing of these data sets, and also processing on demand real time with the scalability, reliability, and throughput. Maybe you want to get maximum out of the system. So one of the things platform is this cloud computing is one of the way to handle such kind of an issues. The other issue is still is the big data collaboration part, because most of the times if you see the data sets in a system, the ownership of the data sets are with various users. So what we required is a kind of an SDI system, which is again should be on a cloud-based platform, which promotes the mechanism of data sharing among agencies, so that the due value for the data sets are provided to the concerned agencies. However, other users should also be able to use them uh, in a scenario where they want to access the data. The third thing which is also important is from the methodology, because as we said, we need to move from a single monolithic system to a distributed system. So what we required is algorithm which are distributed or could run on parallel. Now, not all the algorithm could be efficiently processed in the distributed manner. So that thing also has to be catered to. And then finally, related from the interpretation of the result or visualization, what we also required is uh, looking into the analysis perspective, how best to represent the data sets so that the user is able to represent it. For example, we see in our dashboard example wherein the information that is required by the user could be put in terms of charts and figures which provide interactive mechanism, or in case of points, the points could be clustered, and depending on the zoom level, the necessary subclusters could be formed. So these are the ways wherein these visualizations and interpretation challenges could also be handled with. Okay, so in this session, we talk about the big data analytics. We cover a overview, what we understood what is big data, we understood the characteristics. We also gone through a process of big data analytics. We have seen a typical workflow, and then we have gone into the various tools that are frameworks that are developed from the big data perspective, like Spark and Hadoop, and also the flavors from the geospatial, like spatial Hadoop, RAS daemon, and SQL Hadoop kind of environment, which allows you to use declarative language of processing. And finally, we also talk about a cloud-based, how this cloud computing supports the big data endeavor, wherein it provides the necessary building blocks, wherein the various use cases applications could be built. So here I will stop and I will wait for your questions. Thank you. Okay, so welcome back. So we got couple of questions. We'll take them one by one. There is a question saying how to use big data analytics in QGIS. So think for a while that the QGIS is one of your user interface, and then your as a big data resides on a remote location. I given an example of a raster like a raster based store, and you as a users want to consume it. So think for the terms, as I said, a QGIS as a user interface through which you are able to perform these analysis, because as I said, uh, for to handle and store the data, a single system or a PC may not be a sufficient. So hence the data could resides and on a remote location, and the processing can also happen there. QGIS could be one of the, let's say, the interface or a client through which the user can interact or request data and fetch the data. But most of the processing can happen at the remote end. The second question we got is the what role does cloud computing play in big data GIS analysis? Now, for handling this big data analytics task, what we required is an infrastructure in place, which means we need to have the necessary hardware and also the installation of these frameworks for processing such large and diverse data sets. Now, not all organizations will be in a position to have such infrastructure and also to be able to maintain it over a period of time. The cloud computing in a way provides an option wherein the users could pay for only the amount of time they are trying to use such infrastructure compared to paying a, let's say, the upfront cost of setting up this infrastructure and maintaining it. So the cloud computing provides the infrastructure layer on which the big data analytics could be done. And as I mentioned, there are different models like platform infrastructure service where you can rent a hardware, or we could also have a platform as a service wherein these kind of big data frameworks could be pre-installed, managed by the cloud provider, and we just build the application on top of it. Or we could also have a software as a service like ArcGIS Online or Carto, where we are able to perform GIS operations online. Now there's one more question saying how does a distributed cache works? Now distributed cache, as the name is, cache means storing or caching the information. Now primarily the caching is used to increase the response time for, let's say, various applications. For example, if you're building a web-based applications, storing the information or cache will lead to a faster response time. So there are, again, it is possible to have a distributed cache system on this distributed platform where the memory could be, let's say, kind of assembled in a form wherein the whole main memory appears to the user as one, where the information could be stored. And then primarily the aim is to increase the response time so that the users are able to get the response faster. Now there are again frameworks which allows you to have such system like memcached, redis, and those kinds are the another let's say frameworks which allows you to build such kind of an caching mechanisms. Okay, there is one more question asking how does big data analytics works on Google Earth Engine. So as you mentioned, Google Earth Engines provide a cloud-based platform wherein the data sets, algorithms, and also the infrastructures are available. The various the users can build various use cases as I have shown. Either you can do various urban studies, water related studies, or also glacier retreat kind of an study. So think for a while that all the processing that you are trying to do on a desktop based environment where you follow a typical processing chain of was going to, let's say, the geoportal or the space agency portal to download the different scenes for your study area, followed by pre-processing and before or performing operations on the data sets. So in this way, this cloud-based systems take away this whole process, and you only spend time on working on the area that you're looking for or the solution that you are looking. And such systems are scalable, because suppose you're working a small area, you suppose 2 scenes and 3 scenes you will be able to process, but what if you want to do at the national level? So the whole process chain will be too time consuming a process, and also running on a single system will be taking a lot of time. So in that way, these kind of cloud platforms are much better. Okay, so with this we'll close, and then we'll thanks for your time and patient listening. I want to thank our DLP team here for supporting the lectures. Thank you so much.